Welcome to rankstudent.com, this site used by millions of students around the world for digital education in science and technology. I'm Dr. Ahmed. I will be your host for this brief review of mechanical properties of liquids. What you learn in this chapter will be a benefit in hydraulics, civil engineering, mechanical engineering, aeronautics, and medical studies. For some definitions and properties, fluids have no definite shape of their own. For instance, when you pour water in a beaker, the water takes on the shape of a beaker. A fluid offers very little resistance to shear stress. Fluids are only slightly compressible. For this chapter, we assume that they are not compressible at all. By contrast, a gas is highly compressible. Force and pressure. The force F exerted by a fluid on a surface is normal to the surface. Pressure is defined as force per unit area, P equals F over A. Pressure is a scalar quantity. Its dimensions are ml to the minus 1, T to the minus 2. The SI units for pressure are newtons per square meter. It is also expressed as atmospheres. Another unit is pascals, where 1 atmosphere is equal to approximately 1 times 10 to the 5 pascals. Density rho is mass per unit volume. Rho equals MOV. It has the dimensions of ml to the power minus 3. Pascal's law. The pressure at a given point in a fluid is the same at all points if they are at the same height. At a given point in a fluid at rest, the pressure is the same in all directions. The pressure exerted by a fluid is normal to the surface no matter what the orientation of the surface is. In the diagram on the right-hand side, the pressure on the surface defined by ADFC is normal to ADFC, and similar is the case on the other two surfaces. The pressure under a fluid increases with depth. P2 minus P1 equals rho GH, where rho is the density of the fluid, G is gravity, and H is the height. If P sub A is the atmospheric pressure, the pressure P at depth H is equal to P minus P sub A equals rho GH. This is called the gauge pressure. The so-called hydrostatic paradox states that the height of a fluid column depends only on pressure and not on the shape of a vessel. As illustrated in the diagram on the right-hand side, a vessel has 3 openings A, B, C, different shapes, and yet this interconnected body of a fluid has the same column height in each of the 3 openings. Atmospheric pressure can be measured using a mercury barometer. P sub A equals rho GH, with rho is the density of mercury, G is the gravity, H is the height of the column of mercury. H is approximately 76 centimeters at sea level. 1 torr is defined as 1 millimeters of mercury, which is 133 pascals. 1 bar equals 1 atmosphere, is equal to 10 to the 5 pascals. In a manometer, the pressures at points A and B are equal, as illustrated in the diagram on the right-hand side, and the gate pressure P minus PA is measured by rho GH, where rho is the density of the fluid in the column on the right-hand side. Pascal's law for the transmission of fluid pressure. In a fluid in a container, the pressure is the same at every point. Pressure applied at any point is transmitted undiminished and equally in all directions. So, if you wanted to lift an elephant using hydraulics, you can do so by applying a suitable force F1 on the other arm of a container as illustrated in this diagram. Streamline flow. In steady fluid flow, the velocity of each passing fluid particle is the same. Conservation of mass. The conservation of mass, or the equation of continuity, states that the volume flux or flow rate remains constant throughout a pipe, meaning AV equals constant equals Q, the flow rate, where A is the area and V is the velocity at a location. At high speeds, steady flow becomes turbulent. Bernoulli's principle, an important one. It states that along a streamline, the sum of the pressure, the kinetic energy, and the potential energy remains constant. P plus rho v squared by 2 plus rho gy equals constant. Bernoulli's principle can be used to explain heart attacks due to blockage in the arteries. If blockage causes V to go up, P drops. It may cause an artery to collapse and hence a heart attack. Torricelli's law states that for a container open to the atmosphere, the exit velocity V from an orifice located at depth h from the surface is given by V squared equals 2gh. For a closed container, the exit velocity at a point P2, as illustrated in the diagram on the right-hand side, is given by P sub A plus rho V1 squared by 2 plus rho Gy1 equals P2 plus rho Gy2. A venturimeter measures the speed of fluids. Referring to the diagram on the right-hand side, the following equations you have learned apply here. V2A equals V1A. P1 plus rho V1 squared by 2 equals P2 plus rho V1 squared times A, or A times 2. And P1 minus P2 is rho GH. The velocity V1 can be calculated in terms of the density, the height, and the areas at the two locations, A and small a. A spinning ball causes the velocity of air above the ball to be greater than the velocity below the ball, and hence it causes a lift. Thus the principle used in the design of aerofoils for airplanes. In an airfoil, the velocity of the air above the airfoil is greater, hence it experiences a lift. Fluids have viscosity. The coefficient of friction, coefficient of viscosity, is the ratio eta equals F over A divided by V over L. It is expressed as Poisson, or Newton's second per square meter, or Pascal seconds. Its dimensions are ml to the minus 1, t to the minus 1. Now let's have some fun with the pressures in raindrops. For a sphere of radius a dropping with velocity v through a viscous fluid of coefficient of viscosity eta, the drag force is given by F equals 6 pi eta AV. So let's apply it to a raindrop. Balancing the forces on a raindrop as it is slowed down by viscous drag of humid air 6 pi eta AV equals mg, which is equal to 4 pi over 3a cubed rho minus sigma g, where rho is the density of the water in the drop, sigma is the density of the surrounding humid air. From this equation, the velocity v of the raindrop can be calculated. The equation that you have seen is just a balance of Stokes' law against the force on a drop of rain calculated using the equation F equals ma, force equals mass times the acceleration. Reynolds number defined by rho v d over eta, where rho is the density of a fluid flowing with velocity v, viscosity eta, and d is a dimension of the pipe. It can also be written as rho AV squared divided by eta AV over d, which is the ratio of inertia force to the viscosity force. The flow is laminar for Reynolds numbers less than 1000. It is turbulent for Reynolds numbers greater than 2000. Surface tension is the extra energy that the molecules at the interface have as compared to the molecules in the interior. It is expressed as force per unit length or surface energy per unit area. A method of measuring surface tension is illustrated in the diagram on the right-hand side. From the diagram, the surface tension is equal to mg over 2L, where S is the surface tension, mg is the added weight on the right-hand side, and L is the thickness of the plate, which is the new area created by the added weight. The angle between the tangent to the liquid surface on the inside of the liquid is the angle of contact, illustrated by theta in the diagram on the right-hand side. Balancing the forces along the x-axis, SLA cosine theta plus SSL equals SSA. Theta is an acute angle if SSA is greater than SLA, and is an obtuse angle if SSA is less than SLA. Depends on the surface energies of the liquid, air. The inside pressure is greater than the outside pressure for a drop. It can be shown that P1 minus P2 equals 2 SLA divided by R, where R is the radius of the bubble, SLA is the liquid air surface tension. That's for a drop. For a bubble, there are two surfaces because a bubble is hollow, and therefore P1 minus P2 equals 4 times SLA over R. Surface tensions cause capillary action. For a capillary in water, it can be shown that H rho g equals to S cosine theta over A, where H is the height of the capillary rise, A is the radius of the capillary tube. The height H varies inversely with A. That is the important thing here. I would recommend that to understand the patterns in physical phenomena and to grasp the importance of the definitions and the equations that you have learned, You log on to www.rankstudent.com, download and practice with the thousands of questions, answers, and answer elaborations. They can be downloaded onto your handheld device, such as a mobile phone. Practice helps solidify the concepts, and it promotes critical thinking by making a student recognize patterns in physical phenomena. Good luck and thank you.